Now next topic is unbalanced assignment problem. So what is an unbalanced assignment problem? Whenever the cost matrix of an assignment problem is not a square matrix, that is, whenever the number of jobs is not equal to the number of machines, the assignment problem is called an unbalanced assignment problem. So it is not a square matrix. Number of jobs is not equal to number of machines. So we say that it is an unbalanced assignment problem. Now how to find a solution for such problem? In such problems, dummy rows or columns are added to the matrix with zero assignment cost so that it is changed into a square matrix. So by adding dummy rows or columns, we change it to the square form. Then after getting a square matrix, the usual algorithm, assignment algorithm or Hungarian method, can be applied to the resulting balanced problem. So first make it balance by adding the rows and columns with zero cost. So that it is changed into a square matrix. So dummy rows or columns are added to the matrix with zero cost of assignment so that it is changed into a square matrix. Then apply Hungarian method to get optimum solution. Let us solve one example on this unbalanced assignment problem. So the problem is convert the following unbalanced assignment problem into balanced assignment problem and solve it for minimization. First convert it to balance format. It is an unbalanced. Why it is unbalanced? Look at the matrix, 4 rows, 3 columns. It is not a square matrix. Cost matrix is not a square matrix. So given matrix is not a square matrix. So what we do? There are 4 rows, 3 columns. We want 4 rows and 4 columns. So we add one dummy column D. And what are the cost of assignment? With zero cost of assignment. So that why zero cost? So if you take zero cost of performing all the jobs on machine D, then there is a equal chance of assigning all the jobs X, Y, Z, W to the machine D. So there is a equal chance of assignment. That is, there is a equal chance of assigning 4 jobs, all the 4 jobs to the machine D. So let us make it balance and then we will apply Hungarian method. So we first make the given matrix a square matrix. So we have to add one dummy column with zero cost. So we have added this column D. It is a dummy column and we add this dummy column with zero cost of assignment, so that we can assign any one of these four jobs to this dummy machine. Other costs we keep as it is. First row 9, 26, 15 and 0 is the cost in dummy column. Second row 13, 27, 6 and 0 is a cost in dummy column. Cost of assigning job Y to the machine, dummy machine D. 35, 20, 15 and 0. Last row 18, 30 and 20. So this is a balance assignment problem. The cost matrix is a square matrix now. We say that it is a balanced assignment problem. Now we solve this balanced assignment problem using the Hungarian method. So what is the first step now? Subtract smallest entry of each row from all other entries in that row. So what we observe in the first row, smallest entry is 0. Subtracting 0 will not change the numbers from the first row. Similarly, second row smallest element is 0, third row smallest element is 0, fourth row smallest element is 0, smallest element is 0. So when we subtract 0, elements in all the four rows will not change. So first step will not change the elements in the cost matrix. So we will then apply step number 2. So we have seen that subtracting smallest or minimum element of each row from all the other elements in that row will not change the elements in the row, because in every row smallest element is 0. So we will apply now step number 2. Step number 2 is repeat step 1 for columns. So look at the first column now. First column, what is the smallest number in the first column? Smallest number is 9. So subtract 9 from all the entries in the first column. We get 9 minus 9, 0. 13 minus 9 is 4. 35 minus 9 is 26. 18 minus 9 is 9. Now in the second column, 26, 27, 20. 20 is the smallest number. So subtract 20 from all the entries in second column. We get 26 minus 20, we get 6. 27 minus 20, we get 7. 20 minus 20, we get 0. 30 minus 20, we get 10. Now column number 3, what is the smallest? What is the smallest number? Smallest number is 6. Subtracting 6 from all the entries in column 3, we get 15 minus 6, 9. 6 minus 6, we get 0. 15 minus 6, we get 9. 20 minus 6, we get 14. And smallest element of the fourth column is 0. So 0 will not alter the elements of column number 4. So all entries are 0. Now step number 3. Cover all zeros with minimum number of horizontal and vertical lines. So we apply step number 3, cover all zeros with minimum number of horizontal and vertical lines starting from the row 1. We select the row containing single 0. So first row contains 2 0, second row contains 2 0, third row contains 3 0, fourth row contains single 0. So make an assignment here in the fourth row, and when we make an assignment in a row, we have to draw a vertical line. Now after fourth row, we look at the column number 1. There is a single 0, so we make an assignment in the column number 1, and we have to draw a horizontal line. Column number 2 contains single 0, so make an assignment there in the column number 2. Column number 2 contains single 0, so we make an assignment here and we draw a horizontal line. Then column number 3 contains single 0, make an assignment and draw a horizontal line because we are making an assignment in a row. So in this way, all zeros are covered. All zeros are covered by minimum number of horizontal and vertical lines. And how many lines we have drawn? 3 horizontal, 1 vertical. 4 lines required to cover all the zeros, and it is equal to the order of the matrix. So number of lines, horizontal and vertical lines are 4. 3 are horizontal, 1 is vertical. And it is equal to the order of the cost matrix. So when number of lines is equal to order of the cost matrix, which is also 4, it is a 4 by 4 matrix, then we get optimum solution. So this solution is an optimum solution. Therefore, this is the optimum assignment. Optimum means it will minimize the cost of assignment. So what is the optimum assignment? Let us write down. So X is assigned to the machine A, Y is assigned to the machine C, Z is assigned to the machine B, and W is assigned to the machine D. This is a dummy machine, right? So because it is an unbalanced assignment problem, out of the 4 jobs, first 3 jobs X, Y, Z are assigned to the machine A, C, and D, whereas we will not assign W to any machine because this is not available. It is a dummy machine. Only 3 machines are available. So 4 jobs and 3 machines. Which out of 4, which 3 jobs we have assigned X, Y, Z, and we have not assigned W. So the optimum solution is assign the 3 job X, Y, Z and do not assign job W to get optimum assignment or minimum assignment cost. So what is the minimum assignment cost? The minimum So now look at the assignment X to A, first row, first column. Now where is the cost of assigning job X to the machine A? It is given in the cost matrix in the problem. So cost of assigning job X to the machine A is 9. So C11 is the cost. Then job Y is assigned to C. So second row, third column. What is the cost of assigning Y to C? It is 6. Cost of assigning Y to C is 6. And Z is assigned to B. Job Z is assigned to B. And the cost is 20. W is assigned to D, but D is a dummy machine. So to solve this problem, we have added one dummy machine to get the solution. So the solution is do not assign W to any machine, assign the 3 jobs X, Y, Z to the 3 machines A, B, C, and in that case, the cost of performing these 3 jobs on these 3 machines will be minimum. And do not perform the job W on any machine. So we will add this cost of performing the 3 jobs X, Y, Z on the machine ABC. 9 plus 6, 15 plus 20 is 35. So 9 is this cost of performing job X on the machine A. Y 6 is the cost of performing job Y on the machine C, and 20 is the cost of performing Z on the machine B. And total cost of performing the 3 job X, Y, Z on the machine ABC is 35. And this is a dummy assignment. W is assigned to the dummy machine D. So it means do not assign W to any machine. So this is a solution of the given unbalanced assignment problem.